Good afternoon.
Good afternoon. Good to see you. Thank you. Hello. Good afternoon, Justin. Hello, Andre. Good morning, Marissa. Yes. Oh, and there's more. Sorry. And good afternoon, Eileen. Thank you. And there's more people. Sorry. Okay. Um, yes. Let's see. Yes. Hello. Yes. And I think I said good afternoon. Well, I'll start again. Okay. Good afternoon, Justin. Hello, Andre. Oh, no, what if I started again every time? Then we would literally, that would be awesome. Okay, so I'm going to start again. Good afternoon, Justin. Wait, hello, Andre. Good morning, Marissa. Good afternoon, Eileen. Good afternoon, Erin. Hello, Wenyi. Good afternoon, Rachel. Good afternoon, Kimberly. Good afternoon, Alyssa. Good afternoon, Elijah as Dorian. Good afternoon, Shirin. Good afternoon, Sarah. Good afternoon, Alea. Oh, and sorry, sorry. No, good afternoon, Alea. And there's someone else. Okay. Um, this whole thing about saying the hellos, this is like a story that I think Elijah as Dorian knows about uh, the pianist Richter giving master classes and focusing on one note at it. Well, anyway, all right. Good morning, Jenna. Good morning, Jenna. Okay. Right. It puts a lot of pressure on me to say these things right because if I don't, I think. Okay. Anyway. Yes. Hello. Hello. Okay. I'm already laughing because the world is funny, but because I understand classes are ending on a week from today. I kind of knew that in principle. I've known that in principle for a while, but I'm now knowing it in less than principle or more than principle. So I think that by Wednesday, I will. By this Wednesday, I think I'm. By this Wednesday, you will have the practice document, which really means the rough draft document for your final exam. And this Wednesday will address that directly. I mean, I'm already sort of telling, I mean, I think you already kind of know that it's largely going to be about this Doppler effect business that we keep talking about, but I'll give you the formal document on Wednesday, I believe. And that will allow us to look at it Wednesday and Monday, the last day of classes next week. It will hopefully even have answers in it or solutions or whatever. But I'll address that more directly this Wednesday. Like I am aware we really are getting toward the end. So again, just like and I don't want to spend this whole period talking about it, but I think from here on in, that's what I'm going to, instead of calling it a practice exam, I'm going to call it the rough draft exam, meaning what I'm going to give you Wednesday is essentially will be whatever your final exam essentially is. Any changes between then and the actual final exam, I'll try to update you or make you aware of, on the last class next Monday. But what I give you Wednesday will essentially be what it is that you have to know. And the thing that will be posted, I guess, Tuesday of next week. I'm saying this all vaguely now because this is just starting to sink into my mind, but I understand that your final, my understanding is that classes end a week from today. My understanding is that then final exam period begins the next day and goes through the 25th. So I think more people are coming in. I think you can assume, or you can rely on the fact that your final exam will be posted at the beginning of all that. You'll have the full week to do it. It'll be due like 11:59 on the last day of exams on the Tuesday, the 25th, essentially. And you'll know what's on it by this Wednesday or before that all happens. But a big thing you'll have to do on it is this Doppler effect business. So that's, which I feel like we've now spent a long time on. Let me try to put in perspective for you what I think the punchline is. So hold on a second. Right. Oh, one second. Ooh. for a second. Oh yeah, quick thing too. Sorry, just responding to a private chat about something. A quick thing I don't want to get all bogged down in today. I'm sure you've heard, and it doesn't affect you guys in physics, but it may affect you in science. I'm sure you've heard the rumors, and they are true. You know, everything is being redone for fall for next year. You've heard this, and it's true. Like we went from 90, we were 90% on. All the schedules were done for the fall, as you know, and 90% of all the classes for the fall across the board, John Jay, were, I mean, unofficially 90% of them were some form of online, remote, hybrid. And now there's a new mandate that says we have to redo everything and get up to 60% of our classes to be in person by the fall. Yeah, no problem. And that, I'm sure that's of course causing great confusion and adjustment. And I think it's probably really good news for the long term, but it's obviously very confusing in the short term for everybody, for primarily for students, but certainly for faculty. And so I know you guys are done with physics as of this class, and good, God, Quark bless America, but you have my deep sympathies on how much confusion there must be now about making your new schedules for the fall. And those of you who I'm trying to stay in touch with about your recommendations in graduate school, I still want to, or research, still very much want to stay in touch with you. But yes, now they're trying to push everything sort of back to campus, which of course I think is a very good thing for the long term, but I think is a very confusing thing to be happening right now, the way it's happening. And I don't really know what to say about that other than my sympathies. And I'll also say, no problem. I'll also say, oh God, I say way too much in this forum that I shouldn't say, but you know, I think you guys know also that I have very mixed and thoughtful feelings and thoughts about a lot of things like science and faith and things like that. And I'm very entrenched in both worlds. And so one thing I can just say from being now in a lot of emergency faculty meetings, trying to redo our schedules and trying to accommodate for next semester and trying to offer things, but yet predict what you guys are going to want or need, or, you know, it's all very complicated. Let me just say that, do I want to say this? It is let me say that it seems that in general, from all the statistical data that's been gathered, students in general, statistically, have much more mixed feelings and hesitancy about the vaccination, about getting vaccinated, than the faculty seems to have, the general faculty. I don't, and there's some reasons for that perhaps, and some not. I am a member of the science faculty, a faculty that tends to be, as you might guess, they tend to be more, they tend to be less conflicted about vaccinations than other groups of the population are. I just want to say, I'm very sympathetic to any mixed feelings that any of you might have about the vaccination. Very sympathetic. I find the whole issue very confusing. Okay, as a scientist, as a person who believes other things as well, and I find the whole vaccination issue very confusing. I don't think that there are easy answers. I think everybody should have the right to be confused about it. And I think the only thing that we really know, again, just or what I've learned from science and what I've learned from being a human, is we don't know what we don't know. And anybody who thinks that they know everything about something is, I don't trust. Okay. So what it does seem to be the case is that a lot of things would be made easier and faster and more efficient and more predictable if more people get vaccinated. And that seems to be a big talk among, and it's very easy for a lot of people to say that. But I think it's also very easy for people to not understand why it's not so easy for other people to get vaccinated. And so I just want to register. I mean, it does seem like things are confusing and things are going to keep changing, and we're never going to know exactly how to put together a perfect schedule for the fall. And even if every faculty member banded together to offer to drop everything and offer exactly what they thought was perfect for the fall, whether it's in person or not, we still can't predict what you guys would then sign up for, right? And I know that the predictions would be easier. The predictions would be easier if everyone were vaccinated, but that does not mean that everybody should be vaccinated. That's what I'm saying. Okay. Like, you got to do what you feel you got to do, each one of you, and don't do something just because you think it's going to make things easier on someone else or something like that. I don't know what more to say about it, but that seems to be a thing that's out there. That's my 2 cents on it. Like nobody really knows anything about, or they probably know more than I do, but nobody knows everything. And nobody who acts like they know everything should be trusted. So you, at a certain point, when it comes to issues that are this big, you have to follow your own intuitions. And sure, base your intuitions on data. I mean, try to be as scientific as you can and try to be willing to change your intuitions if you get enough data. But, but then also bear with us as we keep making crazy decisions that keep changing every moment. And that we're sort of trying, we're trying to predict things that we can't predict and then retrofit them. So it's all okay. Anyway, whatever. So let's talk about physics. So the Doppler effect. Here's the deal with the Doppler effect. If there's one, now that we're practiced it a lot and you had time to practice the last period, here's one big punchline that will be on the final exam in one way or another. I think there are 4 cases of the Doppler effect, or 4 basic cases, right? And I think to one of the big implications, well, I'll start writing it. Sorry. Well, what I really think, you'll really know that you not only know how to do the Doppler effect, but you'll know what the point is, or what we're trying to get at, when you come to realize that cases 2 and 4, so to speak, do not have the same answer, and cases 1 and 3 do not have the same answer. And yet there's a big part of each one of us that should have expected that they would. If you, and I'll break this down like right now, but you should know that all 4 cases of the Doppler effect get different answers. But you should also know that that is sort of surprising in a way. And that if you were just thinking about things in a certain kind of if you'd done just enough physics, you would almost expect that 2 of the cases would have the same answer and the other 2 cases would have the same answer, and they don't. And if you can see that, maybe you don't see it yet, but if you can ultimately see why someone might expect, well, all right, so let me start writing this down. But if you can see that, why someone would expect a certain thing and yet it's not the case, then you really do understand a big implication of the Doppler effect. Let me tell you what I mean. Sorry. Okay. I'm gonna look at the numbers for a second to show the point that I'm making here, but just to try to make this as concrete as I can. Like we have 4 cases, right? Let me just fix the view also. I'm sorry. We have 4 cases, right? Like receiver approach, receiver recede, source approach, source recede. So for the moment, let me just almost arbitrarily compare 2 of those cases. Let me compare receiver approach to source approach, okay? And I'm going to assume that all the numbers are held intact. Like the only thing I'm changing is whether I'm looking at like this perspective or that perspective, okay? And so let me even put in the number, like we've already done the numbers, you have them. So let's even remind ourselves of it. Like, and everything I'm about to say, I could just as easily say about source receding versus receiver receding, like it, same conceptual point. But the numerical example that we've been dealing with for like the last 3 days or whatever is we're assuming we're talking about sound. So we're assuming that we're talking about something the speed of which relative to air is 340 meters per second. We assumed that the frequency as measured by the source was, middle A on the piano, which brings us back to Richter, Elijah, is 440 hertz. We assumed that, and we assumed that one of the 2 objects was at rest relative to the medium, i.e., well, we assumed either the source or the receiver was at rest, and we assumed that the other one was coming in at 40 meters per second. So okay. In my mind, this is like case 1 and case 3 or something, but I don't care what number case you call them. In fact, I'm probably flipping that around all the time without meaning to. What I care is that these would be the appropriate numbers for 2 situations that are identical in all respects other than whether it is the receiver or the source that is coming in and approaching the other, right? And notice, I'm sort of being careful about signs here. Like if it's the receiver coming in, I call its speed relative to the medium -40, right? Because it's coming in toward the source. Like whatever it is in both cases, I call the speed of the wave positive, right? And that is a decision that I always make to make all of this consistent and as easy and convenient as possible. It's not a decision I have to make. Excuse me. The decision has to be made. I could make an alternate decision and call the velocity of the wave negative, but that just like causes a lot more negative signs and a lot more confusion. So I always say whatever the wave is doing is positive. Therefore, if a receiver is coming in toward that wave, then the receiver would have a negative velocity, right? Like in that coordinate system. Whereas if the source is coming in toward the receiver, well, then the source would be going the same direction as the wave. So it got a positive 40. Please note that important detail. But having said that, hopefully you can understand at this point that these two sets of numbers that I just chose are the identical situation, except in one case we have receiver coming in, the other case we have source coming in. Now, what I'm saying is, if you look at your notes, or if you do it fresh for the first time right now, or fresh for the first time on the final exam, in both cases, if you're getting used to the Doppler effect, in both cases, what we're always solving for is what is the frequency of this note as measured by the receiver, right? Like that's always the deal with the Doppler effect. We know the frequency as measured by the source, but because there's some relative motion going on, the receiver measures a different frequency, right? And that has like huge implications on the universe that I ultimately want to get to by the end of this course. But whatever the implications are, the point is that the receiver will measure a different frequency, and it's always that different frequency that we're looking for when we do these calculations. Now you're going to tell me. You tell me, and this is kind of a little test here. Please look at your notes now or look in your memory. Because I know we've got it. What did we find for the frequency of the wave as measured by the receiver in the case of receiver approach? I'll give you a hint. It's a number greater than 440, but not a heck of a lot greater than 440. Can anybody, and I think I know it, but can anybody tell me, please, what did we find? So this is what we've been basically calling case one. Thank you. Awesome. I believe that's right. I mean, I just got in the private chat. But awesome. I believe you are right, Mrs. or Mr. private chat person. Yes, the number that I just was told. Okay, wait, now I'm getting to, I'm getting slightly different numbers. I remember this happened last time too. Yeah, you can get slightly different numbers because of chopping off the decimal point, but you get, yeah, there's a slight rounding thing that goes on. That's totally right. But basically, do we all agree? And I think, and it is right in our notes here, but yeah, some things are in the private and some things are in the public. But yeah, we got around, can I say around 492, 494? Do people agree? In fact, I'm even gonna, do people agree? Like, yeah, okay, cool. So I'm gonna say, and maybe even some people said 499, I think, I'm not sure. But yes, we got like 494, 492. And that's what we got for what I'm calling case one, the receiver approach. For tell me, and I'll go back and check in a second too. But in the other case, then I did it really fast. I think I might not have even talked, but I just like scrawled it out in the notes. But you should be able to verify on your own. Same exact procedure. If you solve for receiver recede, what do we get? Right. I think so. That's my memory as well. I mean, it's good. Good. And does anybody else? Oh, I'm saying good because someone's putting in the private chat, and I think, right. Cool. I think technically it is case three. Right. I'm seeing one answer in the private chat that I do agree with. Can anybody else verify either in the private chat or the public chat what we got for the other case? Because we do want you all to be on page with this. Like, again, this is the final exam, or I mean, it's a big part of it. So I do see one answer in the private chat. Does any, or stop me if you don't understand what I'm asking, but I'm asking for the answer to the other case now. Now, we probably didn't do the other case as slowly and methodically with one another, because what I'm trying to tell you all is you do all the cases the same way. Once you get how to do a case, that's how you do it. But you should practice, because you will find, even though it's the same procedure, it does take a little bit of care, and you will find that you'll get slightly different answers for the different cases. So does anybody else want to weigh in besides the one private chat person who's rocking my world right now? For the other, or does anybody want to stop and say we don't know what's going on, or what are you asking for, Yaverbaum, or what vaccination? What? I'm a little, well, all right. I'm going to write down what I'm writing down what the one person in private chat told me, but I don't want to leave everybody in the dust. And here also, I should. These are all rounded, and it is a little. I mean, is this familiar? Oh wait, here. Oh, sorry. Wait. Oh, good call. No, I'm sorry. My bad. Oh, that's really good. The person in private chat is really paying attention. And maybe this is how I just lost you. I don't mean to say receipt. You're absolutely right. No, that is what I'm looking for. Sorry. Hold on. You're absolutely right. What I mean to add, I just used the wrong words on the page. Thank you. That's like a million bajillion points to private chat person who is totally rocking here. The two cases I'm trying to compare right now, the two cases that I do believe we did say in the notes last time, and although yes, one of them we did more quickly than the other, the two cases I'm trying to compare are receiver coming in versus source coming in. I mean to compare two coming in cases, two approach cases. Can anybody, there is one person in the private chat who's totally with me, but and you just pointed out that I just made that mistake. So maybe that's where I lost people. But is there anybody else that can confirm or deny that we got these two different numbers? They're not hugely different, but they are different. Anybody else? Oh my God, I'm totally dying here. Eli, where are you? No, I'm just kidding. Richter, where are you? Just kidding. What am I? No one. Well, I'm going to keep going. I'm going to keep going. All right. Well, I'm going to keep talking, but someone should either I'm still not making sense or I've really lost everybody. And that would be of slight concern because this, we are spending a lot. I'm getting concerned. I may have to, all right, I'll tell you that I'm going to keep talking, but what I might have to do is stop on a dime and ask you all to do this with the two recede cases, like, which I most definitely have not talked through in class. But what I'm trying to say is that once you get how to do this, you do it. Okay, I appreciate the honesty. Oh, okay. Okay, maybe I am. Okay. Okay, no, I appreciate the honor. I just got an honest thing from another person. All right, maybe I'm going too fast. Okay, here's what let me just ask this. Let me back up for a second because I want this to be clear. I'm not trying to yell at anybody, and maybe I thought something that isn't the case. We need to know how to do these four cases for the final. I do believe that we've done at least one very carefully with everybody. If it's true that we've done one carefully, let me pause for a second and ask everybody. Take a moment. Don't even look at my answers here. I'll flip the page to a blank page. I'm going to ask everybody to do this on their own right now because okay, fair enough. I totally appreciate there's another person in the private chat who is giving me a heads up here. Hold on. This is not punitive. This is my bad. Oh, hello. Okay, what I'm asking everybody to do now, and my bad if we haven't done it, but I'm asking everybody to solve this, what I just drew here. Let me try to explain what I'm saying. Like this case that I'm drawing here is the case of the source moving in at 40 meters per second relative to the air. What I believe firmly, and this I do believe, I believe that what we have all solved together somewhat carefully, we all solved what would happen if the receiver were moving in at 40 meters per second. When I say solved, what I always mean by solved is solved for the frequency as measured by the receiver. Like no matter what case we're doing, what we know is the frequency as measured by the source. What we're solving for is the frequency as measured by the receiver. What in all the okay, and these numbers that I'm giving you are the numbers that you had for when the receiver is moving. I gave you a procedure for how to solve no matter what. But the procedure that you did for when the receiver is moving, I want you to use that exact same procedure to solve this, like right now, like everybody, like you don't have to go into breakout rooms or anything, but just try for a few minutes right now to look back in your notes, in this packet of notes that we're looking at right here. Look at what we did to solve for the frequency, the frequency as measured by the receiver. You'll see the procedure I'm talking about. Once you get used to it, you'll see it's actually a very cut and dried procedure in a way. Like what you do is you first solve for the wavelength according to the source by using the frequency according to the source. Then you say to yourself, oh, well, that wavelength that I got according to the source must be the same as the wavelength as measured by the receiver. Like the one thing they're both going to agree on is the wavelength. So you use the given frequency to get the wavelength according to the source. Then you use that wavelength to get the frequency according to the receiver. And it would almost seem like you're just going in a circle, except that the link in each time is velocity. And you'll see that the velocity is not agreed on by both the source and the receiver. So you're not actually going in a circle. So please look in your notes or look wherever, and please don't use that equation that's on the web for Doppler effect. But please, like right now, oh, okay, and I'm reading that, and things are happening in the chat. So, but please, and if you think you got an answer or a question, put it in the chat. It can be private or public. But I need everybody to make sure that they see what's going on. Like, the point is there's 4 different cases, but they're all solved the same way, but they get different answers. And that's the essence of the situation that we need to see with our own hands and eyes. Otherwise, there's nothing to see. Okay, so I'm going to shut up. So please do this now. And if you have already done it, then practice another case. Like if literally you think you've got this solid and you're bored, then literally take these numbers and assume that the source is going back rather than forward and see what you get there. Like just test yourself. But all right, I'm going to start reading the chat. Sorry. Right. I'm saying right to someone in the direct chat. and I'll tell everybody what we're going to do right here, just because there's a little bit of a time factor. I'm responding to people in the private chat, but what I'm specifically waiting for is the minute I get any kind of reasonable answer in the public chat or private chat from anybody that I haven't heard from yet. Like the minute I hear from somebody new, just so that I know I'm not just talking to 2 people or 3 people, the minute I get an answer to this from anybody that I haven't heard from today, then I'm going to assume that's good enough for me and I'll start talking about it. But I want to at least get an answer in the private chat or public. Cool, that counts. Okay, I just got one. Awesome. Hold on. All right. Okay, hold on. If it didn't disappear, where'd it go? Oh, okay. Yeah. So I'm going to start talking in a second. But I'm just now there's a bunch in the private chat. So that's great. I appreciate it, everybody. Oh, and I just lost my entire universe. Hold on. Okay. So I'm just going to respond to these things and I'm going to start talking. But anybody who's still working, still work for a second. Ooh, and someone's joining. Okay. Okay. Things are definitely happening in private chat and again, and this is really, it's really satisfying to my soul. Seriously, like there was a moment there where it seemed like nothing was happening and I was totally freaked out. But then at least one person in the private chat showed me that it was basically my fault. And that's fine. That was clarified. And now everybody seems tons of people do seem right there. So great. I mean, I really appreciate this kind of real communication. I think it's difficult. So, okay, let me say, and I'm going to walk through this now. I mean, I think enough people, and again, I don't mind walking through these things as long as I feel like I'm walking through something that you've all walked through so you can benefit, but it's all just too abstract if people don't try it on their own, right? So first of all, yes, I think what's happening here is that what we should be seeing, what we should be seeing on our piece of paper is if you use the exact same procedure and you use it carefully, and you don't skip steps and you don't make assumptions, and if you're careful about plus and minus signs, you see that when the receiver is approaching, rather than hearing a 440 hertz, they'll hear something like a 492, maybe 494 hertz. But if the source is approaching, then the receiver, instead of hearing a 440, is going to hear more like a 499, 500 hertz. Right? Now, first of all, that's not a huge difference. I understand. It almost might even look like a rounding issue, which is why this is subtle and worth talking about. It might seem like if I'm saying, oh, 492, 494, that's rounding. But now I'm saying 494 versus 499, that's not rounding. You may have good reason to doubt. You might think, well, how do you know one is rounding and the other's not rounding? One easy way to know, it is the case. One is an issue of rounding and the other's not, but why do I know that? Or why would I expect you to believe that? One easy way to tell is if we're believing in this phenomenon at all, if we understand the concept of this phenomenon, that it has to do with relative motion. For example, if we believe that this wouldn't be happening at all if the velocities were all zero, if the source and the receiver were both sitting there in the air, then there would be no frequency shift at all. What the source would measure is 440. What the receiver would measure would be 440, right? But then we gave one of them 40 meter per second velocity, and we observed a shift. We observed that the two frequencies do not agree. What I'm telling you is by that reasoning, the higher we made the 40 number, the faster something is coming in, the more dramatic this effect would be. Like on the next example we do, or on the example on the final exam, perhaps just to make things really vivid, I might, or you might want to try on your own for practice, try 80 meters per second rather than 40. You're going to see the same phenomenon, but you're going to see more dramatic difference among the numbers. And you'll start seeing how it's definitely not rounding. You'll see real difference between the numbers, like the bigger the speed, the bigger the relative speed, the bigger the distinction among the numbers. Okay, that's number one. So 499 is not the same thing as 492. That's the first thing I'm saying. Let me go back. Yeah, so I'm going to this page now. Like, hopefully many of you have just tested on your own that when the receiver is approaching, you get like around 494, which is already different from 440. But then when the source is approaching, you get even more dramatic. It's not only not 440, but it's not even 494. It's like 500. I want to, now that is interesting. That is worth discussion. That is what I want to talk about, but I can't talk about it unless I first believe that you guys got those numbers. Also, before I even talk about it further, since a couple people were now racing through the cases or understanding the cases in the private chat, they started asking me, what about the other two cases? Let me just address like the numbers of the other two cases, because once you get this, hopefully. So similarly, sorry, oh, so is there? I don't know what just happened with the. So I'm not the speaker. Oh, I am. Okay. So, and if you're checking the other two cases, you should get numbers about like what I just wrote here. Again, there is a little rounding, so it's a little confusing. Maybe you got 385, not 386, but there's like a 5 hertz difference, 5 hertz distinction between the two receding cases. Okay. So first of all, just if you're practicing, you should be getting numbers more or less like this. And if you're getting numbers like this, you'll know that you're doing this correctly. But now let me stop and say, like, that is interesting. Let's just back up and look at this. Like 393, 393. Wait, am I doing something wrong? Oh, sorry. Wait, did I go in the wrong direction? Wait. Oh, my bad. Wait, sorry. 393, 393. Oh, I did go in the wrong. Sorry. I don't mean to say 381. I do mean to say 3. I got 391, not 3, but 3 is okay. Yeah. That I don't know if that's the direct chat. Yeah, when I said 381, I mean 391, but yeah, okay, and that 393 is fine. Yeah, no, it's not too different. That's my bad that I wrote 381. I mean to write 391, and 393 is okay. And by the way, again, as I'm saying all this, and you all are showing that you're really paying attention. That's good, and you should be caring about these details. That's good. So either when this is all over today or next time, I mean, next time I'll pick an even more dramatic case, so it'll be even more obvious that where the rounding ends and the differences begin. But yes, those numbers that I'm seeing in the chat are fine for the other cases here. But here's the thing now, conceptually, like, why do I care? Why? I mean, I care that you know how to solve these problems, but also now look, we're talking about, we're saying that if I throw a wave to you while I'm running at you, or while you're running at me, the wave you receive is not the wave that's thrown. I mean, that's what, like, I sing an A, you're going to hear an A only if you're standing still in the air and I'm standing still when I sing it. But if I sing an A while you run toward me, you're going to hear an A sharp. Or if I sing an A while I run toward you, you're going to hear an A sharp, if those music terms mean anything to you, right? Or by that matter, I mean, by that reasoning, if you're following what I'm saying, also we could just say, if I sang an A while standing in the air, but the air were moving, like if there were wind, right? And if the wind were blowing toward you, you would not hear an A, you'd hear an A sharp. That partly explains, by the way, why funny things happen when you're talking to people on the phone in the wind or this or that. Like that is what we're saying. But and I think hopefully you can sort of follow that when you picture an example like standing at the beach. We keep saying, like, if you were to run into the waves, the water waves at the beach, you'll encounter them more often than if you just stood at the beach. I mean, that's the concept that we're saying. We're saying, in other words, what we're saying that this Doppler effect occurs because of the relative character of velocities, the relational character of velocities, that velocity is always a relationship between two objects. It's never a property of one. But here's the weird thing, right? And we're using, when you solve for these numbers, you're literally using that relational quality of velocity every time you say VAC equals VAB plus VBC, or if you say VWR equals VWM plus VMR, you are embracing and deploying the relational character of velocities when you do that. But and so that's all good. Like, in some ways, we shouldn't be surprised that there is a Doppler effect. There's a Doppler effect at all because velocity is relative, but there's a Doppler effect of waves, because only waves have a frequency. Like baseballs don't have a frequency. But here's what's noteworthy about this. To embrace the relational character of velocity is to embrace the idea that if the Earth goes towards the sun at 65,000 miles an hour, that is equivalent to the sun coming toward the Earth at 65,000 miles per hour. Like, right, like we're definitively using the form number 4 of Galileo's principle of relativity. We're definitively using, particularly like I2 and I3, I mean, lowercase Roman numeral I, number 2 and number 3 of the principle of relativity, when we solve the problem, we're mathematically and conceptually deploying this relative character of velocity. Yet, we're finding numbers that say at the end, a receiver coming toward a speaker is somehow yielding a different effect from a speaker coming in towards a receiver, right? Like that's what I'm trying to say here. And you would see that even more vividly if we used a number even greater than 40 meters per second. But we're saying that it makes a difference whether the source is moving toward the receiver or the receiver is moving toward the source. Now that's kind of funny if you think about it, because the whole principle that we're invoking here is that me coming toward you is the same thing as you coming towards me. That there's no objective reality as to whether the source is actually moving through the universe or the receiver is actually moving through the universe. There's no objective meaning to that. There is only how fast is something moving relative to something else. Right. So if I threw a baseball at you, whether I'm running toward you or you're running toward me, I think either way, if I throw a baseball towards you and it hits you in the head, it's going to hurt. But I think we all agree it's going to hurt even more if I'm running toward you while I throw the baseball toward you. I think we would also agree that it would hurt even more if you were running toward me when I threw the baseball at you. I mean, if it hit you, God forbid, cork forbid. And I think we would even be right to think that numerically, like not just conceptually, qualitatively, but precisely numerically, if I throw a baseball at your head, the amount, and it would sort of hurt. If we all agree it would hurt more, like it would have more kinetic energy in joules or in more, like it would somehow be hitting your head faster. If I were running toward you while I threw it, if I'm running toward you at 2 miles per hour, that would increase, like it would increase the speed at which it hit your head by 2 miles an hour. Well, if you were running toward me when I threw the baseball at your head, that would also increase the speed with which this baseball hit your head by precisely 2 miles an hour. Like it's not just a rough qualitative point. I think we would expect, and we would rightfully expect, if we did the calculation, we would find me running toward you or you running toward me when I throw a baseball. Either one would make a difference, but they would make the same difference as compared to nobody running at all. I feel like I'm babbling, but right, like if I threw a baseball at you while I'm running, that is bad. Just like if I threw a baseball at you while you're running, and they would both be equally bad if the speed at which you are running toward me was the same as the speed at which I'm running toward you. That's what I'm. But with waves, with the Doppler effect, evidently, if the source is moving toward you, you get one Doppler shift, a shift of about 54 hertz in this case, whereas, 59 hertz. Whereas if the receiver is moving toward the source, all numbers being held the same, you get a different shift of only 54 hertz, right? And it might look a little bit like rounding, but it's not rounding. If we made a bigger number, we would see even more vividly that it's not just rounding. It actually makes a difference whether the source is going to the receiver or the receiver is going to the source. So I'm saying, what I want everybody to note, and I'm not saying this is wrong, I'm saying this is interesting and worth understanding, that on the one end, we're saying with velocities, velocity of A relative to B should always yield the exact same effect as the negative of velocity of B relative to A. They should just be mirror images of each other. Here, if you have a source moving relative to the receiver at 40 meters per second, it doesn't yield the same numbers as receiver moving towards source at 40 meters per second. Okay. I mean, they both yield a Doppler shift. They both yield a frequency that's different from the source frequency. Both, and that's so people often call the Doppler effect the Doppler shift, meaning there's a shift in frequency, like the frequency as measured by the source is different from the frequency as measured by the receiver. That's what they mean by shift. And I'm saying, yeah, in both cases, whether it's source moving or receiver moving, we get a shift in both cases, and we get a shift in the same direction. Like if the source is coming in or the receiver is coming in, we will get a received frequency that is higher than the source frequency. But the extent to which it's higher is not the same in both cases. That should strike you. What I'm really trying to emphasize, and this is like one of these things in physics, and I see there's 16 minutes left. I'm saying I'm almost trying to break this down to be so clear that you see why you should be confused, if you know what I mean. Like that should almost be confusing. We would almost, based on everything we're saying about the relative nature of velocities, we should almost not expect that. We would almost think, if we've done all of our physics properly to this point and paid attention to everything in physics, if I were asked to predict, what's the Doppler shift if the receiver's coming in, if I knew it was 494, like you guys told me, and then someone said, all right, now predict what's going to happen if the source were moving in at the same speed, I would say, well, I assume it's going to be the same thing, because like, who cares whether the source is going in or the receiver's going in? Like, isn't the whole point of relativity that it shouldn't make any difference? That's what I would say. I mean, and I would almost hope that that's what you guys would say, because that means we've embraced the relativity of velocities. However, that's not what happened. So, and I'm not asking you to explain, I'm about to explain. It's not a contradiction. It's not a mistake, but it means we have to think a level deeper. What's happening is, first of all, if you really did churn through the numbers and you did it our way, if you actually did first solve through the wavelength and you used the GPR form number 4 for the velocities, and then you divided velocity by the frequency. So if you actually did go through the procedure, if you look at what you did, so compare the two cases, go back, compare receiver approaching, compare that to source approaching, you'll see, if you look at your numbers, that what happened in the case of the receiver approaching is that you solve for the wavelength according to the source, and you'll see that you plugged in like 340 over 440, and you got a wavelength. And stop me if this is wrong, or stop me if you don't know where, but please look at your notes of what I'm about to say. When you did the receiver approaching case, you did something like you solved for the wavelength first. And so if you did it properly, you did something like 340, you did something like wavelength according to, I almost want to write it down again, but I'm not going to, I'll write down the other cases. You did something like wavelength according to source is 340 plus 0 all over 440, right? 340 plus 0, meaning when you're solving for the wavelength of the source wasn't doing anything funny in the air. So you did 340 plus 0 over 440, and you got a wavelength of like 0.772 or something, 0.77 something meters, right? Then you went over and you said, aha, that's my wavelength. Everybody's going to agree on that wavelength. Both the source and the receiver will agree on that wavelength. So then you went over to the receiver and said, all right, so the receiver received that wavelength. So I'm going to do V divided by that wavelength. But the V you did according to the receiver, in this case of receiver approaching, you said, 340 plus 40, right? Yeah, technically you did 340 minus negative 40. If you're really being strict about it, you did 340 minus negative 40 all over the 0.77 that you just solved for. So you have like 380 over 0.77, and you got like 494 or something, right? So you got, in other words, a totally expected standard wavelength of 0.77 meters. But then you said, aha, this 0.77 wavelength is coming in to an object that's rushing in toward it. So the object, the receiver, is seeing this regular everyday wavelength coming into it extremely fast. So he actually receives that wavelength more frequently than it was sent, and you got a number higher than 440. But then when you looked at the other case, when you did when you did source approaching, you follow the exact same procedure, right? So you solve for the wavelength according to the source, and there you say, okay, I'm solving for the wavelength. So you do V over F, and you said there, V equals 340 minus 4. Well, technically you did 340 plus a negative 40 all over 440, right? And so you got a wavelength of like 0.681 or something like that. And then you took that wavelength and said, okay, everybody agrees with the wavelength. Everybody agrees with this wavelength. So now I'm going to go look at the receiver who's getting this wavelength of 0.681, and the receiver is just standing still. So you did 340 plus 0 over 0.681, and that yielded a frequency of like 499 hertz. Please make sure you're following along with me. Like, please stop me if anything I said just contradicted or confused like you. But if you're following me, and if that's the way you did the two different cases, you'll notice you did the same procedure, but step back and look at the physics of what's going on. What you're really saying is what you're saying is that in the two different cases, there's two different wavelengths. Like, and this is a subtle thing. I'm saying we always care about the wavelength because it's what everybody will agree on in the situation. Like, whatever wavelength the source sent is the wavelength that the receiver got. No question about that. That's why we use the wavelength, like, on both sides. But if you compare the two cases, the two calculations you just did, what you're actually saying correctly is that in the case of the receiver moving, in the case of the source standing still in the air, they send out a wavelength that is the everyday customary wavelength. Like, nothing interesting is happening with that wavelength. It's just 0.77. Literally, in other words, that is the wavelength of a middle A on a piano under normal conditions. Anytime anybody plays middle A on a piano, if it's a 440 hertz sound that escapes from that piano, as long as the piano is just sitting still in the air and as long as you're just standing still in the air, what comes to your ear is 0.77 meter wavelength. That's what you solve for in that case. But then you're just saying that the receiver is running in toward that wavelength so fast that it hits them more frequently than 440. In the other case of the source approaching, you are literally saying that the wavelength is compressed. You're not saying that anybody's disagreeing on the wavelength, but you're getting a new number for the wavelength. You're saying it's no longer a 0.77 meter wavelength. It's 0.681 meter wavelength from the moment it comes out of the speaker, right? Because the speaker is making this sound. This is the whole thing that waves do that particles don't. The speaker's sending out this sound at 340 meters per second, but running toward it as it makes the sound. So it sends out like one crest, right? And then it keeps running. So by the time the next crest comes out, it's already a little bit closer to the first crest than it would normally be. Like, it's not just standing there letting crest comes out, it's racing after its own crests. And we can literally close the gap between crests because they don't care how fast we're going. They're just going out at some speed fixed by the air. So in your second case, which I think we're technically calling case 3, but in this case of source approaching, the reason we have to be really careful about these calculations and do the V very carefully each time is you're saying, if you do it correctly, that right from the get-go, the wavelength that came out, like the wavelength that came out of this speaker is smushed, smaller than it would normally be because the speaker is running toward it while it makes it. So it's what textbooks will call a compressed wavelength. But then that compressed wavelength travels to the receiver. It's not compressed like compared to the receiver or something. Like, the receiver will also agree. The receiver's also getting a 0.681 meter wavelength. It's smaller than it would usually be, but it's not smaller than the source thinks or something like that. Both the receiver and source, in other words, will agree that they got a wavelength that's smaller than usual or smaller than expected because that source is running into the air, whether the receiver knows it or not. I mean, and you could even say the receiver could figure that out from the fact that it was a compressed wavelength. So then this compressed wavelength is going along toward the receiver, but the receiver is just standing there waiting for it. The receiver's not doing anything interesting. The receiver's just standing there and gets this compressed wavelength traveling at 340 meters per second. So since it's a smaller distance between the crests come more frequently. In other words, in both cases, in both approach cases, what the receiver gets, he or she does get more frequently than what the source sent, but it's actually for two kind of different reasons in the two cases. In one case, a regular wavelength is sent out and then we're running to meet it, so we get it more frequently. And in the other case, we're not running to meet the wavelength, but the wavelength that's sent is a compressed wavelength. So it's actually, if you were look, and this is one of the reasons we make you do the Doppler effect this way with this one procedure rather than just this like blind plugging and chugging that is sometimes done by Chegg. I mean, on the web. I mean, by Elijah Asdorian. I mean, by Richter. I mean, I'm just kidding. But no, the reason we make you do it this way is I really want you to see the physics of it. That I would think if I weren't breaking down the physics, if I weren't like actually investigating all the steps, I would just think source coming into receiver, receiver coming into source, what could possibly be the difference? Like I believe in relativity. They're going to be the same. But what I would not, and that still sounds right every time I say that, I still feel like, wait, shouldn't that be right? It should be right. But why it isn't, what we're actually telling ourselves if we look at these steps step by step this way is what we're realizing is, oh, yes. Velocity is still relative. Absolutely. Velocity is always a relation between two things. But what this whole Doppler effect is really trying to highlight for us is velocity always has to have two things being compared. One of those things is always what we call the frame of reference, for sure. But here's the deal. If I throw a baseball to you, right? If I throw a baseball to you, the reason that you coming toward me or me coming to you is exactly the same either way is because those are the only, other than the baseball, those are the only two objects in town. There's me and you. Me coming toward you or you coming toward me is the same thing. Once I throw a wave at you, it's not about me and you anymore. It's about me to the medium and the medium to me, or you to the medium and the medium to you. In other words, relativity is still correct. Me to the medium is exactly the opposite of medium to me. That's why when you're plugging in carefully and stuff, if we say that the velocity of the receiver relative to the medium is negative 40, then the velocity of the medium relative to the receiver is positive 40. Like we absolutely are following the principle consistently. It's just that now we have to honor the fact that there's a third real to life actual entity in the discussion. There's a third frame of reference. It's not just about source and receiver. It's about source, medium, and receiver. So the relativity of velocity applies to source, medium, medium, source, or receiver, medium, medium, receiver. And so much so that if the source moves through the medium, all of a sudden the wavelength gets compressed and then gets sent at a regular speed to the receiver. But if the receiver moves, then the wavelength does not get compressed, but does get encountered by a moving object. Like that's how much of a difference the medium makes. This is why there's a Doppler effect for sound and other waves, but there's no Doppler effect for baseballs because baseballs, whatever they're doing is not fixed to any medium at all, even if, and I'll say this, even though of course baseballs move through air, like it's not like we're saying baseballs don't go through air, just like sound goes through air. But air is not acting as a medium when baseballs go through it. Air is not making the motion possible. If you took away the air, a baseball would only move that much faster. You can throw a baseball in outer space, no problem. But air is not something that's just slowing down or intruding sound. Air is making the sound travel possible. Take away the air and you don't have the sound anymore. Hence, it's quiet in outer space. Like that's what this is trying to emphasize. Let me just look at the time. Oh, it's 3 minutes. I hope that, and that's what we're going to try to like test you on the final exam. I mean, again, I will publish by Wednesday somehow or other. I'll give you the rough draft of the final exam. I'm not trying to hold you in suspense, but it's going to look a lot like this. Like you're going to compare the 4 cases and you're going to have to sort of discuss why they are all different. But whatever pattern I just said about the receivers is exactly the same. I mean, I'm sorry, whatever pattern I just said about approach it's the same concept for recede. So the numbers you get should correspond. Hopefully this is sort of clarifying. Let me also, since there's 3 minutes left, let me also tell you, because it's been a rough semester, it's a rough year, it's rough times. We can't pretend this is exactly the same as it would be if we were all in class together at school. Like, oh, good. Oh, wow. Oh, that's great. Okay, good. I'm very glad to hear that. And hopefully you'll feel even better when you get the actual document, but good. No, I'm glad to hear that. And let me, and again, look, with the 2 minutes, I feel somewhat apologetic. I can't pretend that I will have shown you every single thing that I would normally show in a regular class. And I can't expect you guys to have engaged in I think you guys are doing great, but we all do have to understand this is a little bit different. It's not a normal semester. And therefore, we're not getting to every single thing, and I apologize, but but I am insisting that you get to a punchline with all this. I want you to see why this is all cool and relevant no matter what. So one thing I want to say as a foreshadow right now with the 2 minutes, but I'll develop this more in why this is particularly interesting is if ever you have any reason to convince yourself that light sometimes behaves as a wave, and yes, that's the thing I'd like to try to convince you of before the course ends. And yes, normally I would have more time to do that in a more assiduous way. But let me just throw out there that if you've ever been given any reason or evidence whatsoever or if you just intuitively somehow sense that you think light behaves like a wave, and again, we will talk about that for the last couple of periods, but if you were to ever believe that light is a wave, okay, then this whole concept would apply to light as well. And frequency, the final will be posted essentially probably Tuesday the 18th. I will be more exact on that as we get closer, but it'll be posted either Monday night the 17th or Tuesday the 18th. Essentially at the beginning of finals, and you'll have the whole final period to do it. It'll be due 11:59 on the 25th. That I can tell you. But sorry, so with the 1 minute left, or the 30 seconds, just consider this. If light is a wave, and sometimes it is, then frequency of light is interpreted by the human brain as color rather than pitch, right? And you know this from chemistry and other things, right? So lower frequency light is like red, 5 times 10 to the 14th hertz vibration of light is what we interpret as the color red, and a slightly higher frequency is what we consider orange and yellow. And okay, so just to throw out there, if this effect happens with light that comes from stars, which it does, if it turns out, if you had evidence to believe that the light that you receive from stars is being measured on Earth as more red, like more toward the red end of the spectrum, then it would be measured if in the frame of reference of the star, which is a whole complicated thing, how we would know that. But if you could just even consider the premise that when we get light from stars, and we have a way of measuring the frequency of the light that we get from stars, and we also have a way of predicting or knowing what the light would be, what the frequency would be measured if we were in the frame of reference of the star. That's called spectroscopy, right? And you know a bit about this from other classes. And again, if you could just consider the premise for a moment, if you could consider the possibility that when we get light from stars, it tends to be measured by us as more toward the red end of the spectrum than we believe it would be measured if in the frame of reference of the star. That's called the red shift. It's the Doppler shift of light, or the Doppler effect for light. We tend to receive light frequencies from stars at lower frequencies than we believe they would be measured from the stars themselves, or than we believe they were sent. If you believe in that data, or if you've ever heard of that data, if you've ever heard that there's a red shift of stars, it's for exactly this reason. And the thing is, if you believe this reasoning, and if you have any reason to believe that light does travel as a wave, then then the fact that there's a red shift, which there is, this does happen. The fact that we receive light at redder frequencies than we believe it was sent is what tells us that stars on average are moving away from us all the time. We get the light at lower frequencies than it was sent because there's a Doppler shift going on, because we infer, since we already believe the Doppler effect and test it with sound, we believe that since we keep getting light colors to be more red than what they were sent from the stars, we infer from that on average, typically stars are moving away from us. It's a source receding phenomenon. And that's where we get the idea of the expanding universe and the Big Bang and all of that. Like, it's very heavy, it's big implication stuff. It's why I care about the Doppler effect. It's like the Doppler effect is why we believe in an expanding universe, which is a very weird thing to believe in. But all right, I went 3 minutes over time. I'm so sorry. We'll pick up on this Wednesday. We'll talk more about the final exam Wednesday. Oh, sorry. Sorry. No problem. Oh, awesome. Okay, no, awesome. Thank you guys. But I'm keeping you. No, awesome. Thank you. Thank you. Okay, bye. Bye. But I got it.